Today's lesson is 7.2, Exponential Growth and Decay Models. When a real-life quantity increases by a percentage over a period of time, the final amount can be modeled by this function right here, where A is my final amount, P is my initial amount, R is the rate or the percentage at which it grows, and of course, T up here is time in years. This part right here, 1 plus R, is known as my growth factor. You'll know it's a growth factor because it has a plus in it. This is how I know that I'm growing, okay? When a real life quantity decreases by a percentage over a period of time, it changes to this right here. A is going to be the same. A is going to be my final amount. P is going to be the same, the initial amount. R is still my rate or my percentage. T is still time. And then this factor here, 1 minus R, is my decay factor. And you'll know it's decay because you will see the minus in there, okay? What's going to be the difference that you know if it's growth or decay is this number here in the parentheses. If it is less than 1, it's going to be decay because 1 minus a rate is going to give me a 0 point something. And if it's more than 1, it's going to be a growth because you're going to see 1 point something. That's how you're going to know the difference, okay? So we've got a couple of examples today, and we're just going to go ahead and write our equation, and then we're going to go ahead and plug it in the calculator, and we're going to figure it out. So the population of Coleman, Texas, grows at a 2% rate annually. If the population is 2,000, if the population in 2000 was 5,981, what would be the population in 2010? Round to the nearest person. All right, let me go ahead and change that. That should say in 2000 was 5,000. Okay, so here we go. I can already go ahead and start setting up my equation. So A equals the initial amount was the 5,981. We are growing. It says right here that it grows at a 2% rate. So I already know to use the 1 plus. Now I have to take 2% and I have to go ahead and I have to change it. Okay, so I knew that P was 5,981. I know that the rate is the 2%, but I have to go ahead and change that. I have to move the decimal 2 times, so I'm going to think of it as 0.02. And of course, it said the time was from 2000 to 2010. That's 10 years. So I'm going to go ahead and use 10 right here. I'm going to go ahead and pop this into my calculator. Now you can pop it into the Desmos calculator just like that, or you could go ahead and you could do the addition of the 1 plus. I just want to show you in case the Alex gives it to you like this. This is exactly how I know that it's a growth because notice right here, I'm seeing that 1 point. I'm not seeing a 0 point. Okay, I'm going to just pop this into my calculator, and my calculator is going to give me my answer of 7,291 people. Remember, people, we have to round it up every time. So whatever kind of decimal we get, we have to go ahead and round up. All right. My cat. All right, here's another real life problem. You deposit $1,000 into a savings account that pays 2.5% annual interest. Find the balance after 3 years. If the interest is compounded A, annually, that means once a year, B, monthly, that means 12 times a year, and C, daily, that means 365 times a year. So here we go. Let's start with our rate. Our rate is the 2.5%, but remember you're moving that decimal to 100%, right? So you're moving it here, and it's going to be 0.025. My beginning is the $1,000 that I put into my savings account, and my time is going to be 3 years, and then I'm going to use the three years to help do the months and then the days. Okay, so 3 years, and then months, it would be, let me see, months we would do 12, and then we would, or well, we're going to have a different formula. Sorry, we're going to have a different formula. All right, here we go. So annually. Let's do annually. Yes, Leah. And let's see which one gives me the best outcome. So 1 plus 0.025, and I'm going to raise it to the 3 years. Okay. Remember, you could go ahead and you could think of this as 1,000 times 1.025. You could put either one of those into the Desmos calculator, and they're going to give you $1,008. And if I round the change, 18 cents. Okay, so after 3 years of savings, I'm going to have an extra $8.18. Not bad. I have more than I started with. Now, when I go ahead to start compounding it monthly, I have to think of a little bit different of a formula. It changes just slightly. My cat, she's stuck in the bedroom. Oh, I have a new variable. And my new variable is n. N. Okay. N is going to be the number of times the interest is compounded within the year. I know, right? Compounded, guys, just means that it's being given more money. Okay. So for this one, for part B, where we're going monthly, N is going to be 12. There are going to be 12 months in each year. P is going to stay the same. Here we go. So I start with my $1,000. R is going to stay the same. R is going to stay the same. And here I'm going to do 12 times 3. Now, if I go ahead and stick this in my calculator, I get 1,000 and I get 1.002. And of course, this is 36. If I put this in the calculator, I end up with $1,077.80. Not bad. I think that's a little bit better of a deal for me personally. Now for the last one, C, where we're going to compound it daily, I'm going to use that same new formula with the N, and N is going to be daily 365, right? Because there's 365 days in a year. Now, I've been told that what banks do is that they use 360 because they say there are 12 months, and each month has 30 days, and 12 times 30 is 360. So that's what I've been told that banks actually do. So banks actually shortchange you 5 days. I go try to find a bank that doesn't, right? Because you're going to get just a few pennies less. Now, honestly, I would just go ahead and put this all in here because there are 1, 2, 3, 4 zeros. Right, Leia? I want all my money too. Mm-hmm. And I put that into and I get $1,077.88. So honestly, is there much difference between daily and monthly? Not really, 8 cents. I think the monthly one is the way to go. It's gonna make sure that I ensure that I get all my money because in all actuality, uh, with the bank, these two are probably the same, right? They're probably exactly the same. All right, let's take a look at the next one. You buy a new car for $35,000. There's my brand new car. The value of my car decreases by 12% each year. Notice here, now we're talking about decreases. We're going to talk about decay for this one. What is the value of my car? What will it be in 5 years? So let's go ahead and let's talk about what my principal is. So, sorry, what my initial cost was. My initial was the 35,000 that my car cost. My rate is the 12%, right? Which of course, remember is 0.12, because you've got to move the decimal from the end, 1, 2, we're talking about hundredths, right? So 100%, you've got to move it back. And T, my time, is going to be the 5 years. So here is my problem. P is 35,000. 1 minus my rate, because we're decaying, to my time t, which is 5. Now, what I want to show you right here, guys, is that when I subtract, right, when I subtract, I end up with 0.88. This is how I know it's decay if I just see the problem written. This is how I would know that I have decay because it starts with a 0 instead of a 1, okay? I'm just going to go ahead and I pop this into a calculator, and this really hurt. $18,470.62. After 5 years, that's how much my car is worth. All right, our last one today. The half-life of an isotope of barium is about 10 years. The half-life of a substance is the amount of time it takes for half of that substance to decay. So we're going to use our decay formula one more time. If a nuclear scientist starts with 200 grams of barium, there would be my initial amount. How many grams will remain after 100 years? Now, this one is exponential. Anytime we talk about a half-life, we're going to be doing an exponential decay. So let's think back to that first lesson that we had at the beginning of the week, and let's think back to this formula. Okay, let's think back to that one. Now, A is going to be, let me put it over here. Oops. A is going to be the 200. B is going to be my base, which is the half-life, so it's 1/2. X minus H is my rate, and so that's 100 divided by 10, or 10. Okay, it's the 100 years, but remember every 10 years is when it goes in half. So I had to divide the 100 years by the 10 that it takes to go in half. And of course, my K, there is no K. There is no K in this case. So I have 200 times 1/2 to the 10th power. Okay, or I could think of it as 200 times 1 over 1,024, which either way, whichever one of these two that you put in the calculator, you could put this in the calculator or you could put this in the calculator, right? Either one of these could go into a calculator and you would get 0.195 5, and of course it would be grams. That's how much would be left after 100 years.